Thank you for the introduction. So today I'm going to talk about this ongoing work called the Stereographic Barker's MCMC proposal. So this is joint work with my collaborators. So yesterday I'm making the slides. I was able to find one picture for all of them. So if you see this person on the right-hand side, that's Chris. If you didn't notice it, this is the same person as the chair of this session. And the person on the left-hand side is Gareth sitting behind. So you can see he looks very happy and very young, and no gray hair, and not wearing a tie. So the person in the middle, super good-looking person, is my PhD supervisor, Jeff Rosenfeld. So the idea of a Markov chain Monte Carlo is very simple. So you construct a Markov chain. So the stationary distribution of the Markov chain is designed to be your target distribution you want to get a sample from. So when you run the MCMC algorithm, there are roughly two phases. So the first phase, you start this Markov chain from some initial state, and you run it for a certain number of iterations. And what you hope is after this number of iterations, the distribution of the Markov chain is close enough to your target distribution. So you can start to use the output of this algorithm as a approximate sample for your target distribution. So the first phase is called the transient phase, or burn-in. So maybe the most important question to ask in this first phase is the mixing time of the Markov chain. But we still have the second phase. That's we call it stationary phase. So in the stationary phase, we start to use the sample from this algorithm. So the key question to study is what's the quality of this sample? For example, that corresponding to how efficient this Markov chain can explore the state space. Right? So in this talk, I will talk about both efficiency and the robustness. But by efficiency, basically, we'll talk about two things. The first thing is whether this Markov chain is geometrically ergodic, or even better, if it's uniformly ergodic. And the second property I will talk about is optimal scaling. That's scaling with the dimension of the state space. I will particularly mention consider maximizing expected square jumping distance. So this optimal scaling, roughly speaking, corresponding to the stationary phase. So the idea is if your algorithm has, on average, a larger jumping distance, then the output of your algorithm has a less correlation. So you produce a better quality for the samples. And I will also talk about the robustness. So by robustness, I will have three types of robustness. So the first one is robustness to tuning parameters. Because many MCMC algorithms we use, they have some tuning parameters. And usually, if you tune the tuning parameter very well, the performance can be very well. But the problem is some algorithms may be very sensitive to tuning, which means in practice, it's very hard to learn how to tune this algorithm. So we need some robustness to tuning. It's a desirable property, which means this algorithm in practice is easier to tune. And also, I will mention robustness to the tail of the target distribution. So I have two types of tail. One is called a heavy tail. So in this talk, I mean the tail is heavier than exponential tail, but lighter than Cauchy tail. And the other type is robustness to super light tail. So here I mean the tail is lighter than Cauchy tail. So the outline of this talk is as follows. So at the very beginning, I will give a very brief review of some gradient-based MCMC algorithm. For example, like the previous talk already mentioned, the unadjusted long-driven algorithm, or ULA. And the second algorithm is called the Metropolis adjusted long-driven algorithm, or MALA. So then I will focus on the third algorithm, which is called Barker's proposal. So this is based on a paper by Sama and Giacomo. I think both of them are in the audience. So basically, the first part, I will just review existing gradient-based algorithms. And then the second part, I will switch the topic. I will mention this a new, relatively new framework called the Stereographic MCMC. So this is a new framework to design new MCMC algorithms. Then I will introduce one existing algorithm called the Stereographic Projection Sampler, or SPS. So this existing algorithm is not a gradient-based MCMC algorithm. Then finally, I will introduce a new algorithm called the Stereographic Barker's proposal. So this is a gradient-based MCMC algorithm. So from the name of this algorithm, you can imagine what I'm going to do is really simple. I'm just combine this Barker's proposal by Sama and Giacomo in this framework called the Stereographic MCMC. So basically, that's the new algorithm. So this new algorithm has some good properties, but because this work is ongoing work, we haven't finished all this theory, so I won't be able to show you any rigorous theory in this talk. So this talk is guaranteed to be a very light talk. Okay. So the first Markov chain is called ULA. So this is a very simple Markov chain. So if we look at this Markov chain called X, so based on the current location xt, the next location of the Markov chain, we first have a deterministic move using this gradient of log target density. So here pi is my target density. And then I will add a random walk. So in this Markov chain, I only have one tuning parameter, which is the step size called h, which also appear in the variance of this random walk. So this ULA is very popular in recent years in machine learning theory community because I think partly because the proof technique is very beautiful because they can connect to optimization literature. So I'm a big fan of all this existing recent theory papers. But in this talk, I will try to mention if you are being more pragmatic, in order to use this Markov chain in practice, perhaps you need to know a lot of property of your target distribution. For example, they have several issues for this Markov chain. The first issue is the stationary distribution of this Markov chain is not your desired target distribution. And this is clear because this is Euler-Maruyama discretization of Langevin diffusion. And the second issue, if your target has a heavy tail, then at the tail region, this gradient term is too small, so it kind of disappears. So this Markov chain behavior is really become a random walk. So the convergence of this ULA is very slow, so it's not geometrically ergodic. And the third issue is if you have a target which has a super light tail, then at the tail region, this gradient term dominates other terms, so it's too large. So this ULA just overcorrects the tail, so it becomes oscillating. So this ULA is even transient. And finally, this like a simple Markov chain, I only have one tuning parameter h, and it's also sensitive to tuning. For example, this is a very toy example. Suppose your target distribution is standard Gaussian, and then you run this ULA, then it will be oscillating if the step size is larger than square root of 2. But if it's smaller than square root of 2, suddenly the oscillating disappears. So hopefully by the end of this talk, we will solve all of these issues. So the basically the high-level idea. So we will solve the first issue basically using a Metropolis-Hastings framework in the rest of the talk. So which guarantee the target distribution is the stationary distribution. And for the second issue, heavy tail target, so we use the idea of a stereographic MCMC. And for the third one, super light tail, we use this Barker's proposal. And finally, the robustness to tuning come from both the robustness of stereographic MCMC and also Barker's proposal. So let's have a look at the second algorithm. It's called MALA. So this is Metropolis-Hastings algorithm, and it's also very simple. Basically, we use ULA as a proposal. So we first compute a proposal, then we add the accept reject step. So this, of course, solves the first issue and also has a very nice properties. So this paper by Roberts and Rosenthal, they prove this optimal scaling, which scale with the dimension as order d to the 1/3. However, this algorithm doesn't solve other issues. For example, if your target has a heavy tail, the ULA proposal at the tail region is just like a random walk proposal. So this MALA just behaves like a random walk metropolis for heavy tail distribution at the tail region. So it's not geometrically ergodic. And when the target has a super light tail, at the tail region, this ULA is transient. So it's proposed very crazy proposals. And you can see, because we add this accept reject step, So this proposal will very likely be rejected. So the mala will be stuck at the current location because most of the proposal will be rejected. So the convergence, again, will be very slow. So the mala will not be geometrically ergodic. And finally, this mala also sensitive to tuning, and this was studied by this paper by Sam and Giacomo. So I'm using this picture from their paper. I think what they studied is they changed the scale. So they consider a target with a 20 dimension, and they changed the scale for the first coordinate. So the gradient in the first coordinate direction has a different magnitude compared with the other direction. And they studied this expected square jumping distance when they changed the proposal step size. So you can see this mala, which is this red color triangle line, is very sensitive to tuning. So there exists algorithms that propose a robust version of mala. So actually, in the original paper by Roberts and Tweedy, they actually recommended another version for mala where the gradient is truncated. So there are also other existing papers here, but in this talk I will just focus on this Barker's proposal. And one reason is this Barker's proposal is a robust version of ULA proposal without introducing any new tuning parameters. But most of the other algorithms, they they improve the robustness by introducing new tuning parameters. But turns out this robustness perhaps will be sensitive to this new tuning parameters. So what is this Barker proposal? So this is also a very simple proposal. So this is a one-dimension case. So basically the proposal is as follows. So you first generate a random walk called Z. But then you can decide to propose working forward or working backwards. And you use a probability to decide that, and the gradient is used in this probability. So you can see if the proposal is in a good direction, it's the same direction as the gradient, then this probability will be larger than half, which means more than half probability you will propose to move forward. Otherwise, you propose to move backwards.
Backwards with respect to Z, which is itself be backwards.
Oh yeah, like the reverse version of that. So you can see this algorithm actually there's a red color term. If this color term is very small, actually you can do some Taylor expansion and to see this proposal density for this proposal Y. Actually, they matches ULA proposal density locally. So this first order actually matches, which means if this red color is small, this proposal really behaves like a ULA proposal. But if the red color term is large, for example, you increase this gradient, for example, goes to infinity, then this probability becomes either 1 or 0. So you can see the proposal density will become the absolute value of a Gaussian. Right? So you can see this from this picture. So this base kernel is the Gaussian density. And if you increase the gradient, the density becomes a kind of absolute value of Gaussian, right? But in the middle, if the gradient is relatively small, the proposal is really like a determinist move in the gradient direction and then a Gaussian density. So this is a one-dimension version. So how about extended to a high dimension? So the original paper has two versions of the Barker proposal in high dimension. So the first version, I will call it naive Barker. So this is another version the authors recommended. So this is a straightforward extension of the one-dimension Barker to high dimension. So basically, you first propose a random walk in high dimension, and then you can decide to work forward or backwards, the sign of this walk. And then the probability you use is really in the product of this random generated proposal, random walk and the gradient direction. So this algorithm won't work well in high dimension. The reason is in high dimension you generate a random direction. This is almost always almost orthogonal to the gradient direction. In that sense, this inner product term is relatively small, almost always very small. So this probability is very close to half. So in that sense, the proposal density is close to random walk proposal. The gradient information is not fully used in this proposal. So I did some simple simulation. So this is expected square jumping distance for different acceptance rate. As you can see the picture in the middle, so this dot line is the random walk metropolis. And this blue line is the naive Barker proposal. So this naive Barker proposal is slightly better than the random walk metropolis. But if you look at compare with the gradient algorithm, for example, Mala, or this later mentioned this coordinate-wise Barker, so they have a different scale with the dimension. So if you change the dimension, this two jumping distance separate, which means they have a very different scale with the dimension. And for the acceptance rate, for gradient-based algorithm, usually they have this 57% optimal acceptance rate, which is corresponding to the maximum expected square jumping distance. And for random walk metropolis, we know the optimal acceptance rate is roughly 23%. And for this naive Barker, this optimal acceptance rate seems to be closer to 40%. So right now we don't know exactly this number. So this in the conjecture perhaps is 38% or something, but we don't know how to prove it now. So it's an open problem. So the other version of high-dimensional Barker proposal, I will call it a coordinate-wise Barker. So this is also a very simple proposal. We basically use the one-dimension Barker independently to all the coordinates. So in other words, for different coordinate, you generate a one-dimension Barker proposal. And the gradient you use for each coordinate is the gradient component at that particular coordinate direction. So you can see the gradient will be used in all the coordinates in this sense. So this is like the Barker proposal works well in high dimension. So there's a small issue here. So it's not hard to see this proposal density actually depends on the choice of a coordinate system. For example, in this picture, this is a two-dimension picture. Suppose you have a target distribution on the right-hand side and your current location of the Markov chain is here. Then the proposal density for this coordinate-wise Barker, you can see the gradient direction is horizontal. So for the second coordinate, the gradient component is 0. So the proposal is basically a random walk proposal in the second coordinate. However, if this situation happens in a high dimension, for example, the gradient direction is in the direction of the first coordinate, but all the other d-1 coordinate, there's no gradient component. Then this proposal actually reduced to the naive Barker proposal. Because the gradient information only used in the first coordinate, but because this Barker proposal can automatically truncate the gradient, but all the other coordinates, there's no information for the gradient, so it won't be used the gradient for the design of the proposal. So in that sense, this coordinate-wise Barker proposal, you kind of hope the gradient of your target by your choice of a coordinate system will most likely in a relatively good direction, in the sense that it has a similar component in all the coordinate, most of the coordinate directions.
Yep. Can't you take a random direction, randomized direction?
Yes, I think so. But in the original paper, they didn't recommend it. But in the algorithm, you have to be able to do two things. One is you have to be able to evaluate the proposal density because the accept and reject step. So you have to have a way to choose a random coordinate system in order to be able to evaluate the proposal density. Yeah.
This would be an issue with Mala as well.
No, Mala doesn't depend on coordinate system because it's a gradient direction move and then add a Gaussian, and the Gaussian is isotropic. So if you rotate the coordinate system, you still have the same gradient direction, right? For example, if you rotate this picture, right, you still have the same gradient direction. So you move deterministic that, and then you add a Gaussian. The Gaussian is rotation free, like a invariant. But keep in mind, the goal of this Barker proposal is to propose a robust version of Mala. In that sense, we kind of hope, if the gradient is not, the magnitude of the gradient is not crazy, we hope this Barker proposal density is closer to ULA, right? And only truncate the gradient when the gradient magnitude goes very large. Okay, so there's a very nice property of this Barker proposal. In this paper by Yuri Vogrik and also Simon Giacomo, they prove optimal scaling for this coordinate-wise Barker has the same order d to the 1/3 as Mala. But if you look at their result, they have this maximized expected square jumping distance. Compared with that distance for Mala, there's a loss of a constant for the jumping distance, roughly 2.5 times constant loss. So the order scale with the dimension is the same, but the loss of a constant. So I don't have a proof, but it's reasonable to believe this loss of a constant is because the gradient is not always in the good direction. So in that sense, the proposal density sometimes very different from ULA. So that's the efficiency get lost because of that. I have to say this optimal scaling theory usually prove using a family of distribution, which is a product ID target, if you are familiar with the theory. And for that family, actually coordinate-wise Barker or coordinate-wise algorithm, is a favorable class. So in that sense, this result perhaps is a pretty good for coordinate-wise Barker algorithms. However, this Barker proposal won't solve the issues for heavy tail because in the heavy tail region, the gradient disappears, right? So that's they have the same issue. However, it gives a really robustness to tuning and also super light tail. So this is a very nice picture from another paper by Max Hurd. I think he's also in the audience. No?
Not today.
Oh, not today? Oh, yeah. Sorry. So this picture basically shows what's the difference between the Mala and the Barker for the proposal part of it. So suppose the current location of the Markov chain is X, and it has a proposal density called QXZ, and it generates a proposal called Y. But if it is a target distribution on the left-hand side, it has a super light tail, then the reverse proposal density, because you have to evaluate this for the accept and reject step. Right, so this location Y, the gradient is really large, so the proposal density is really far away. So what's the proposal density from Y to X? It's very small. So this proposal would very likely to be rejected if you use Mala. But compared with the Barker proposal, because the gradient is automatically truncated, so the backwards like a proposal from Y to X, this proposal density QYZ is very reasonable. Right, so it has a very large density at X. So that's why this Barker proposal is more likely to be accepted. So I think that's all I want to talk about other people's work. Right, so this is a review of like work is not done by me. So now I switch the topic to a new framework called the Stereographic MCMC. So this original paper is not a very new paper. It's on the archive at least 2 years ago. So this is a very simple idea. So the idea is instead of design MCMC algorithm in Euclidean space, we first do a transformation and transform this Euclidean space to a compact set. So in this picture, is the compact set is a sphere. Then we just design MCMC algorithm running on the sphere to sample a transform target. And then we map everything back to Euclidean space to automatically get an MCMC algorithm sampling my original target. So that's basically this idea. So it's a really simple variable transformation idea. So in this picture, this is a classical like a transformation called the stereographic projection. So you can see this stereographic projection almost define a one-to-one mapping between Euclidean space to the sphere. For example, you can imagine this is a sphere put on the Euclidean space. So for any point on the Euclidean space, you can draw a line to the north pole of the sphere, and they uniquely intersect the sphere with one point. So you can just map this point on the Euclidean space to this point on the sphere. And similarly, you can map any point on the sphere to one point on the in the Euclidean space. The only point you don't have this one-to-one mapping is the North Pole. So we just need to add one state to the state space called infinity, and this define a one-to-one mapping. So we basically use this idea. We first transform the target to this on the sphere. Then we run a Markov chain on this sphere to target my transform target. Right? So that's basically the idea. So here is the algorithm in the original paper called the Stereographic projection sampler, but it's really just a random walk metropolis algorithm, but designed using the way I just described. Right? So this algorithm is very simple. So suppose that the current state of the Markov chain in the Euclidean space is at small x. So I want to propose a random walk proposal. But instead of a proposed random walk proposal in the Euclidean space, I first do is using stereographic projection to project to one point on the sphere. I call it Z. Then I will do a random walk proposal on the sphere. So what I'm going to do is suppose the current location after transformation for my Markov chain is at this point Z. So I will do in the tangent space a random walk, Gaussian random walk with a proposal variance. It's also a tuning parameter. And after this random walk in the tangent space, I got this point, blue color point called Z plus DZ. But this point is outside of the sphere. So I will do a renormalization just to make it back to the sphere. So this Z hat is my proposal on the sphere. So you can imagine this is the simplest way you can imagine for doing a random walk proposal on the sphere. And this Z hat will be my proposal on the sphere. So I can use the stereographic projection to project it back to Euclidean space. So I got this Y in the Euclidean space. That's my proposal in the Euclidean space. Okay, and then I will do the rest is standard. I will do the metropolis Hastings to accept this proposal with a certain probability. So this probability has a new term, which is basically the Jacobian of this stereographic projection. So here I have another tuning parameter called capital R. That's the radius of the sphere. So in this picture, I'm using a unit sphere. So the radius is always 1. But when I project to Euclidean space, I will choose the radius. So I make the radius larger to the radius equals some tuning parameter capital R, and then project to Euclidean space. So you can see this algorithm have two tuning parameters. One is subsize, like a local proposal subsize in the unit sphere, and also the radius of the sphere when I project to Euclidean space. So that's the basic algorithm. Yeah.
This makes moving in the original space that are very inhomogeneous. If you're on the top of the sphere, you're going to move like crazy.
Yeah. So you can see by this transformation, right? You basically map all the tail region to a neighborhood of the North Pole, right? So in that sense, if you run a Markov chain like near the North Pole, the project back Markov process speed up very fast at the tail region. Okay, so you may ask why am I going to do this? So why I want to design random walk metropolis but using a transformation, right? So
can I ask you just so that how you should, this depends on the radius of the sphere that you pass.
Yes.
How do you decide that?
Yeah, so this radius is a tuning parameter right now. So I haven't talked about how to choose that. But I will talk about this is a tuning parameter. So I will talk about robustness to tuning. So this turns out this SPS is like a stereographic version of random walk metropolis compared with the Euclidean version of the algorithm. It has a very nice property. So the first property is ergodicity. So we can show this SPS is uniformly ergodic for even a heavy tail target. So if you allow to slightly change the standard stereographic projection to some other version of the stereographic projection, actually we can show the SPS is uniform ergodic as long as your target has a tail lighter than Cauchy tail. So this is like ongoing work with Sebastiano Grazzi. I think he used to be at Warwick and now he moved to Bocconi recently. So compare with this SPS, this Euclidean version of algorithm as random walk metropolis is never geometric ergodic for any heavy tail target. So basically, you get a uniform ergodicity for free as long as your target has a tail lighter than Cauchy tail. And the second property is convergence bound or optimal scaling. So we can basically show this SPS scale with has a convergence bound basically linear with the dimension under certain conditions of the starting initial state, even for heavy tail target. So I missed the talk on Monday by some power, but I think I believe he mentioned this random walk metropolis version has this convergence rate linear with the dimension when the target is satisfied, for example, strongly log concave or some functional inequality. So this is basically we can establish something similar, but for a much larger family of target. So really go beyond the log concavity. So this is the basic joint work, ongoing work with Federica from KTH in Sweden. And in the original paper, we also show this optimal scaling result. So we can do compare this SPS by the maximum expected square jumping distance and compare with that distance to random walk metropolis for the same family of distributions. And we can see this jumping distance for SPS is always no smaller than the maximized jumping distance for the random walk metropolis. And then finally, I want to talk about robustness. So both random walk metropolis and SPS, because they are not gradient-based algorithms, so they are robust to super light tail targets. And this we know the random walk metropolis is very robust to tuning. And maybe kind of surprisingly, this SPS is even more robust to tuning than random walk metropolis. And the reason is for the SPS, you have not the reason. For SPS, you have actually more tuning parameter than random walk metropolis. For example, you have this local subsize H, and you also have a radius R. And if you want to do, you can also introduce another tuning parameter, which is the location of the sphere, right? And here we have a result. Basically, we can consider this is a robustness result. It's really an optimal scaling result. So we can compare this maximize expected square jumping distance for SPS and this ratio compared with the random walk metropolis. So if this ratio is larger than 1, means SPS is better than random walk metropolis. So in this paper, original paper, we show this ratio can be written as 1 divided by 1 minus alpha times beta times gamma. So alpha, beta, gamma is some constant that are from 0 to 1. So you can see if alpha, beta, gamma, one of them equals 0, then SPS has the same performance of a random walk metropolis. And if all of them are very close to 1, this ratio can be arbitrarily large. Right. So what is alpha, beta, gamma? So this alpha is a penalty for the misspecified radius capital R. So basically, it's another tuning parameter. So if you choose a tuning, this like a radius R tuning parameter larger or smaller than the optimal one by a factor square root of lambda, then this alpha becomes this function of lambda. So you can see lambda equals 1, this alpha will equals 1. Right? But for any lambda, this alpha is always between 0 and 1. So this so it won't change this ratio. This ratio always no smaller than 1. And what is beta? Basic beta is a penalty for mislocation of the sphere. So it basically is some variance and divided by second moment. So you know this variance equal to second moment if the mean is 0. So basically that's corresponding to if the target has a mean 0, or you put the sphere at the mean of your target. So if you don't do that, you choose a location of the sphere which is not optimal, then you suffer by some factor beta, and it's just the variance depending on like divided by the second moment. And finally, this gamma is a distribution specific penalty. So it basically measures how close to anisotropic distribution of your target. So it equals 1, for example, for Gaussian target. But if your target is not close to anisotropic, then you have a constant gamma here. And also the optimal acceptance rate for tuning the other tuning parameter, local step size H also is to tune it to get the optimal acceptance rate 23%. So basically this is the robustness for tuning. So I think I motivated why we want to do a gradient-based proposal, but using the stereographic projection idea. So if you look at the existing non-gradient based algorithm, this SPS dominated random walk metropolis in many aspects. But the scaling with the dimension is still the same. It's linear with the D. But we have all this robustness result. So we really want to improve this SPS by introducing the gradient in the proposal to improve this linear with the dimension to the order D to the 1/3 for Mala or for coordinate with Barker. So basically that's the motivation of this talk. Okay, so before I introduce the new algorithm, if we want to extend the Mala or naive Barker to this stereographic MCMC framework, is quite straightforward. The reason is, if you remember this SPS, what the algorithm is, the proposal is in tangent space, and we propose it in the tangent space random walk proposal. And if instead of this random walk proposal, you propose a ULA proposal in the tangent space, or you propose a random walk, then you pick the sign, then you automatically get a stereographic version of Mala and also stereographic version of naive Barker. However, these two algorithms are not the algorithm we want. The reason is for the stereographic naive Barker, as I said, the gradient information is not fully used for the design proposal. So we expect the performance may be similar to SPS. But for the stereographic Mala, the reason is if you remember the stereographic projection, it basically maps all the tail region to the neighborhood of the North Pole. So actually, for the transform target, at the neighborhood of the North Pole, the gradient is unbounded. So it's very similar to the super light tail problem. So at the neighborhood of the North Pole, this stereographic Mala may stuck there because all the proposal in the tangent space are ULA proposal, they will be rejected. Okay. So that's the reason that we really want to do this stereographic coordinate-wise Barker proposal. So what's the difficulty for this new algorithm? Like first of all, as someone already mentioned that, so this coordinate-wise Barker really need a coordinate system. However, there's no global coordinate system on the sphere. However, is it possible we just use a local coordinate system for all the tangent space? Actually, it's possible because this coordinate system is used only for two things. One is to generate a proposal, and the other is to evaluate the proposal density in the accept reject step. So if we have a local coordinate system for all the tangent space, actually we can both generate a proposal and also evaluate the proposal density. However, this problem is how should we choose a local coordinate system for all the tangent space? Because I don't want to choose a local coordinate system naively. For example, my gradient in my tangent space in the direction of the first coordinate, right? So that in that sense, my coordinate-wise Barker perhaps just behaves like a coordinate, like a stereographic naive Barker. Right? Okay.
Why do you need a local coordinate system? You can just intrinsically just run motion on the sphere, right, and take a proposal from that.
Well, so Brownian motion on sphere is like random walk metropolis. That's like SPS, right? But if you want to do like a Langevin diffusion on the sphere, then it's like a stereographic Mala. It has a robustness problem at the neighborhood of the North Pole. If you discretize it, right? If you discretize it.
I'm just wondering why you just want to can't just stay on the sphere.
Yes, but later you will see my solution. I really try to avoid the local coordinate system. Yeah. Later you see the algorithm. I try to avoid using local coordinate system. At least I need a coordinate system, but I try to avoid the computing local coordinate system. The reason is this Barker proposal in high dimension. The best version is coordinate-wise. And my motivation is to use it because it's a robust version compared with the other proposal, which doesn't depend on coordinate system. For example, this ULA proposal. Is it answer your question? Okay. But I need to find a kind of a automatic and good way to choose a local coordinate system that guarantee that my gradient direction in that local coordinate system is in a good direction. So my coordinate-wise Barker can the proposal can be robust and also close enough to the ULA proposal. Finally, I try to avoid compute this local coordinate system. The reason is if I have to compute the basis vectors for that d-dimension Euclidean space, then I have to compute a d by d matrix, right? If that's like I have to do that, then my algorithm definitely will involve a matrix multiplication or matrix inversion. So I will try to avoid any matrix multiplication in my algorithm. So in other words, I need to find a way that I can compute a coordinate-wise Barker proposal without using basis vectors like a matrix multiplication. But at the same time, I need to guarantee that my gradient in that coordinate system is always in a good direction. So basically, we solved this using one idea, and this is the very simple idea, and basically it's the only new idea in this talk. So this is the idea. So we use a very simple formula. This is called the Givens rotation formula. The basically says in the high dimension, if you have two vectors n1 and n2, they are also normal, and you want to compute a rotation matrix that rotate a vector by angle theta in the space spanned by these two vectors, then this is the rotation matrix. So the good property of this rotation matrix is if you use this rotation matrix to rotate any vector, this rotation doesn't involve a matrix multiplication because it can be reduced to like inner product of vectors. So in other words, the computational complexity for this rotation is linear with the dimension. But in general, if you use a rotation matrix to rotate any vector, the computation is like a quadratic of the dimension. So basically, we'll just use this Givens rotation to compute the coordinate with the Barker proposal and satisfy all these properties I mentioned. Okay, so this is the most important slide. So basically describe what the algorithm is. So suppose the current location of the marker after the transformation is at this point. And this like a tangent space at that point is a green color, and there's a gradient, like a gradient direction. That's the gradient of my transform target. And so what I'm going to do first, I will do the first Givens rotation to rotate this tangent space to the tangent space at the North Pole. So this rotation, you can see, it doesn't really depend on the gradient. It only depends on the current location of the Markov chain on the sphere. So after the first rotation, I got this blue color, like a tangent space. So in this blue color tangent space, I have a gradient direction. So my second rotation is, I will look at this direction, and I will rotate this gradient to a fixed direction. So this fixed direction, at this point, it doesn't matter what it is, as long as this direction is fixed. So after this 2 times Givens rotation, I got this red color space, where my gradient is always in the fixed direction I picked. So now I can give a coordinate system to this red color space to guarantee that this gradient is always in a good direction. And then I can use this red color coordinate system to propose my Barker proposal, coordinate-wise Barker proposal, using only the magnitude of the gradient. Because the direction is always fixed, so only the magnitude matters. Right. After I compute the coordinate-wise Barker proposal, there will be one point in this space, the red color space. Right? Then I will rotate this point back to the original tangent space by 2 times of reverse rotation. That give us 1 point in the original tangent space, that is a green color tangent space. So this point is my proposal in my original tangent space. So basically, this is the algorithm. And similarly, you can also evaluate the proposal density because you just need to do is rotate twice to this red color coordinate system and evaluate the proposal density in this red color system. So that's all this algorithm. I hope it's clear. So yesterday when I make this slide, I was wondering after this slide, perhaps some of you are not very convinced that this is a valid algorithm. You want to see perhaps the algorithm like formally written down. So I have the following slides. It's very easy to read. So this one. So basically, you define some rotation matrix and then you compute the proposal using the rotations. So I counted yesterday, we need 6 times of a rotation. The reason is for computer proposal, you need 2 times the reverse rotation. But the second rotation is using the gradient direction in the space of like a tangent space at the north pole. That direction, you need a first rotation from the original tangent space to the tangent space at north pole. So in total, you need 3 times the rotation. And in the accept and reject step, you need to evaluate the proposal density that need another 3 times the rotation. How much time do I have?
About 0 minutes.
About 0 minutes. Wonderful. So finally, I will show you a very simple simulation. So this is really a toy example. So the target is 100-dimension Gaussian target. So this is the anisotropic target. So it's really the best target for stereographic MCMC. So I run the 3 algorithm. That's a stereographic version of coordinate-wise Barker. That's the proposal. The proposal algorithm. So sorry for this picture. It's an old picture. I used to call it the magic Barker, so because I really like this Barker proposal. And the second algorithm is a stereographic naive Barker, and finally is a stereographic Mala. So for this twist plot, this is the y-axis is the latitude on the sphere. So it's basically the latitude for the sphere, and the 0 is corresponding to the equator. So this is corresponding to the stationary phase for this target. Because the target is anisotropic, it's a really nice target for stereographic MCMC. So actually, all these algorithms satisfy a property called blessing of dimensionality. So the missing time actually decreases with the dimension. So converge very fast. But we can still compare the acceptance rate for these 3 algorithms because if the proposal using gradient, the acceptance rate tend to be larger. And for this naive Barker on the sphere, so we have a roughly 77% acceptance rate. And this number is very similar to SPS for this particular target. And for the proposed Barker and also the stereographic Mala, they have acceptance rate larger than 90%, because they use a gradient in the proposal. So the second simulation, so for this particular example, all these 3 algorithms, they start from the south pole. So they start from the latitude equals -1. So the next example, I will do the same simulation, but I will start all these 3 algorithms from the north pole. So this is basically the result. So you can see the first 2 algorithms basically behave similarly. For the proposed Barker proposal, they have like a larger than 90% acceptance rate. However, for stereographic Mala, it's stuck at the North Pole because the ULA proposed density is keep being rejected. So basically, that's everything I want to say today. Thank you.
Questions for John?
So the multiple problems with Mala, for regular Euclidean space, the Gaussian would be okay if you tune the steps well enough. But I guess you're making the tails lighter in some sense here. Do you know for what's the heaviest tail target for which you might have a problem here?
You mean for the stereographic Mala? No, I don't. Basically, you are asking ULA.
So if it's on a Euclidean space, right, if the tails are lighter than Gaussian, then that's when we know the gradient's not Lipschitz. But somehow this transformation is changing things.
You mean for the transform target?
Yeah.
So what's the light tail version?
Exactly.
Yeah. I can only say for the traditional stereographic projection. Sure, yeah. For the traditional stereographic projection, so the gradient at the North Pole become unbounded. It's always unbounded, but it becomes like a peak density at the North Pole when the target is lighter than the tail is lighter than the star, like a multivariate student TV degree freedom equals D. Right? But we solve this issue by
They are heavier, right? But the question is here the opposite one for the light tails when the gradient explodes.
for the light tail in the Euclidean space.
So in Euclidean space, the gradient grows faster than linearly when you're lighter than Gaussian.
Yeah. So for this issue, I think Mala I think for this issue. For this issue, then the gradient at the North Pole is almost always unbounded for any tail. So the Mala always have this issue. Yes.
So the North Pole, the tail is heavier by a polynomial factor, right?
The North Pole, sorry?
At the North Pole, the tail is heavier sort of by a polynomial factor.
What do you mean the tail at the North Pole?
Well, as you approach the North Pole, okay, we can.
Let's go.
Yeah.
So I'm sorry, I don't have a question on the Parker, but the S Mala, similar to Sam, but it seems like it might be more effective, at least in this case, to move the current state in your original Euclidean coordinates from x to x plus h by 2 gradient log pi, and then map this point into your sphere, and then do a random walk proposal around it. And that would then be probably not have this issue happen.
If you want to save this Mala algorithm, yeah, I think I agree. Because the random walk part is on the sphere, so it's also speed up but the gradient part, I think the gradient part corresponding to on the sphere, you do a very small move, a gradient move. So in that sense, it seems to kind of truncate similar to truncate the gradient for the transform target on the sphere.
But a small move on the sphere might be a big move in the original space.
But you do the gradient move in the Euclidean space, which is corresponding to a very small move at the neighbor of North Pole. So you have the same like you get kind of ignore the gradient at the neighborhood of the North Pole. You of course you can do that. I would say this framework. If you look at this, you don't really have to choose this direction, right? So you can choose any direction, and you can choose a different direction for different area. It's the same as long as you know. For example, you have a partition in the neighborhood of the North Pole. You will choose this fixed direction to be the direction of the first coordinate. It basically means you always automatically propose locally naive backer when it's near the North Pole. But it's far away from the North Pole, you can do the coordinate ones, the best coordinate ones backer. So in that sense, also you can do this. You can do adaptive MCMC by tuning what's the best direction you should use for different area.
Last question, maybe. Okay, so let's thank Jun.